Remember to start recording again. There we go. I'm going to try to do two more problems where we solve these by factoring, and then we're going to move on to using the square root method. I made a decision at break. We're going to try to get out of here about 8:15 tonight. So if anybody's expecting or needing a ride and expecting to be picked up, you might want to fire off a text or slip out quietly and make a call to let them know. I'm going to try to make a hard stop at 8:15, and at least we got a fan now, but maybe they'll get us some air working. Okay, let me go back to the document camera here. There it is. All right, this one looks a little bit different than the ones we've been solving. Does everybody agree? Everybody take a look at it. Tell me if you agree that this one looks different. And what makes it look different, obviously, is this isn't just x squared anymore, right? It's still a quadratic trinomial. It's got a second degree x term, first degree x term, a constant term. It's already set equal to 0 for us. But we can no longer say, oh, just draw some parentheses and put x at the start of both of them. But let me say this. There are things about factoring this that are like the ones we've been doing. So let me tell you what's the same. There's some things that are different. That's what makes this problem a little trickier. But here's what's the same. It is still true that the first terms in the two sets of parentheses have to multiply to give you this first term, 6x squared. But there's more than one way to get 6x squared, right? You could do sheets of paper. So you could try 6x times x. That would give you 6x squared, right? So that's possible. Or you could also try 3x times 2x. That would also give you 6x squared, right? Now, I think those are the only two ways. But, you know, if this was 12x squared, maybe you start with 12x times x, or 6x times 2x, or 4x times 3x. And so you can see that if there's a number, you know, other than 1 in front of that x squared term, it makes it trickier already, because while it's still true that these first terms in the two factors have to multiply to be that first term, there could be several different possible ways to get that, depending on how many different ways this number can be factored, right? If it was 24x squared, then we'd have to decide, is it going to be 24x times x, or 12x times 2x, or 8x times 3x, or 6x times 4x, and so you can see how that can get more complicated. But at least we know it's got to be one of these two ways, because those are the only pairs of things you can multiply to get 6x squared. It is also true that the last numbers are going to multiply to be this last number, positive 12. There's only so many ways to do that as well, right? But here's what's not true anymore. Let's say I did this. Let's say that I think it starts with 3x times 2x. And let's say I'm just going to try a couple of numbers that I can put here that would multiply to give me positive 12. Now, I can figure out, I think, that they have to both be positive. Remember, they have to both have the same sign if they multiply to be positive 12. Here's what's not true anymore. Those same two numbers that multiply to be 12, they will not add to be 17. That's what makes it harder, really. So let's say I put 3 and 4 here. I mean, 3 times 4 is 12, right? If this worked like the other problems did, we would expect that if I foiled this, I would get plus 7x in the middle. Because remember, I'd multiply these numbers 3 times 4 to see that the last number would be 12. Then I would just add these two numbers to see what the middle number is, and 3 plus 4 is 7. But if I multiply these, I'm not going to get 6x squared plus 7x plus 12. See, 3x times 2x does give me 6x squared. Let's skip the outside and inside parts of FOIL for a minute. Let's just go to the last times last part of that. When I do last times last, 3 times 4 is positive 12. So we know those things work. But look what happens when we do the outside and inside parts of FOIL. we don't just do x times 4, which gives us 4x. We're doing 3x times 4, which gives us positive 12x. And we're not just doing here 3 times x. We're doing 3 times 2x, which gives us positive 6x. And 12x plus 6x is positive 18x. That's what we'd get in the middle if we tried to factor it this way. Do y'all see that? So obviously that's not correct, but I just wanted you to kind of see why it's a little trickier to factor these. So let's take a look at how we can factor it. There is a method. You could just guess, by the way, and there's nothing wrong with doing that. So like if we go back to that, where we did that, it didn't work, we could still keep trying stuff. I mean, we could still just keep trying other things until we see what works. We could try, for instance, plus 12 and plus 1, because 12 times 1 is 12. Or we could try, now this is something to think about. Notice I used the same 2 first terms and I used the same 2 last numbers, but I'll get 2 totally different answers if I FOIL these, right? Because now it matters, and here I'd get 3x plus 24x. Here I'd get 27x in the middle. Here I'd get 3 times 12 is 36. 2 times 1 is 2. I'd get 36x plus 2x, which is 38x. It'd be different, right? But you could try this, then you could try 6 and 2 and 2 and 6. Then you could try 3 and 4 or 4 and 3. And of course, if none of those worked, then you could go to 6x, to starting with 6x and x. And you could run through those same possibilities, 1 and 12, 12 and 1, 6 and 2, 2 and 6, 3 and 4, 4 and 3. You could just do that and see which one works, you know, FOIL them to see which one gives you the correct thing. Nothing wrong with doing that, and if you've learned to factor that way, and some of us have, if you've learned to factor that way, you might be pretty good at doing it like that, and that is often how I factor, because I've practiced it so much over the years, because I've been forced to, obviously, in my job, that I've just gotten really good at it. But I'm going to show you, I'm going to try to show you a method. It's not the only method for doing this. It may or may not be the best method for doing this, but it's the method that I teach because I'm always teaching college algebra. And so I have students who are coming into this class needing to know how to factor these, because technically that's a prerequisite skill for this course. But oftentimes students don't know how to factor it. So I tried to figure out the method that allows me to explain to you how to do it in a way where you can see how to do it, and hopefully it's repeatable steps that can give you a chance to learn it faster if you don't know how to factor these. I'm saying that to say this: if you already know how to factor this, if you learned a method in high school for factoring these, and you actually learned the method and you actually remember how to use it, that's fine. But the other popular method, by the way, this method I'm using is not popular. It's actually not widely known. But the popular method for doing this requires you to also know how to do something called factoring quadratic trinomials, quote, by grouping. And that's a whole other skill that we would have to take time to learn. And we just don't have that time in a class where this is supposed to be review material. But we're going to do as much review as we can. So we're going to do 2 of these problems. I'm going to try to go slowly through this. Be careful as we're doing this. Be careful that you're not so intent on taking notes that you're missing what we're doing. If you're looking down while I'm doing stuff, you're going to miss the stuff I'm doing, and you're going to miss the whole thing. So you've got to balance your note taking with your watching what's happening. Now, with that said, if you already know how to factor these things, you can just chill out and not pay attention at all, because you already know how to do it. But if you don't know how to factor this, watch this closely. So when you factor these things, and again, you shouldn't need to do this unless you've got a number in front of that x squared term, other than it being just 1x squared. So here's what we're going to do. We're going to start by multiplying 6 times 12. You always start that way. The first number, the coefficient of the squared term, times the last number, the constant term. So that is 6 times 12. Now, I'm aware that 6 times 12 is 72. And if you've been taught a method by a high school algebra teacher, they started by doing this because every method requires it. Mine is going to kind of veer away from theirs here in a minute, but you always do this. But they probably told you to literally multiply. They probably literally told you to write the number 72, 6 times 12. I don't do that. The reason I don't do it is because I'm counting on a factor tree that we're going to put together in a minute to make me not have to do that. But you could. It doesn't hurt anything. So we multiply 6 times 12. I'm not going to write 72 because you'll see in a minute why that doesn't matter. But here's what does matter. It was positive 6 times positive 12. So whatever that number is, it is a positive number, right? So I'm going to put a plus there to remind me of that. You'll see why in a minute. If this problem, y'all look, if this problem had been 6x squared plus 17x minus 12, I would still multiply 6 times negative 12. I would still just write 6 times 12 here, but out here in parentheses, I'd put a minus to remind me that that was positive times negative, and this actually is a negative number. Y'all see what I'm saying? The reason I don't really care specifically that this number is 72 is because all I want is the factor tree for whatever this number is. So if I went ahead and wrote 72, the first thing I would write under it would be 6 times 12 because I would want to do its factor tree. So to do the factor tree, well, you can obviously start by saying, well, 6 times 12, whatever that number is, it's 6 times 12. And 6 is 2 times 3. And of course, I can't go any further there. 2 and 3 are each prime numbers, right? And 12 is whatever. I'll say 4 times 3. You might have said 6 times 2. It doesn't matter. You just keep going as long as you can. So then 4, I can go farther with that. That's 2 times 2. I can't go any further with the 3. So now I can't go any further. 2, 3, 2, 2, 3. Those are all prime numbers. I can't break them down further. If you look at what I'm going to call the roots of that factor tree, we've got 2, 2, 2, 3, 3. I'm going to write that down. 2 times 2 times 2 times 3 times 3. Now, we've talked a little bit about this in this class. This factorization, 2 times 2 times 2 times 3 times 3, is called the prime factorization of this number. Again, I recognize that number is 72, but I don't care. The reason I don't care is I need to use, well, first, let's do a quick recap of what we've done so far, which isn't that much. We started by multiplying the first times the last number. Coefficient of the squared term times the constant term. We made note of the sign of that number. It's positive times positive, so that is a positive number. But all we did is broke it down to its prime factorization. Okay, so now listen real carefully. I always draw a couple of blanks with a comma between them to remind myself now that I am looking for 2 numbers. Now listen real closely. I'm looking for 2 numbers that when multiplied, y'all look where I'm pointing, that when multiplied give me this number back. Here's why I don't care specifically that that number is 72. When I put my 2 numbers together, I'm going to use every one of these prime factors somewhere within those 2 numbers. So for instance, maybe I want to do it this way. Maybe I want to take 2 times 2 is 4 for one of my numbers. Well, if I use 2 times 2 is 4, that used up those factors, then all these other factors I'd have to multiply together. 2 times 3 is 6, 6 times 3 is 18 to be my other number. Y'all see what I'm saying? You have to use every one of those prime factors somewhere in the 2 numbers. it is guaranteed that these two numbers will multiply to be the same as whatever this number is. It's easy to see. 6 times 12 is 72. Guess what? 4 times 18 is also 72. Why? Because we're using the exact same prime factors, right? We've just arranged them differently. But here's what I know. I need two numbers that multiply to be this thing, which means that I've got to use every one of these prime factors somewhere within those two numbers. And because that's a positive number, they have to have the same sign. Here's the kicker. Now listen real close. Those same two numbers have to add to be this middle number. Well, right away, I can see that this possibility is not correct, because 4 times 18 is this number, positive 72, but 4 plus 18 is 22, not 17. Y'all see that? Everybody with me? But I can see that they have to both be positive numbers. They have to have the same sign because they multiply to be this positive number. Those same two numbers add to be positive 17, so they have to both be positive. So look at those prime factors and tell me what the two numbers are I'm looking for here. Eight and 9 is 8 and 9. That's it. And in this case, it shouldn't, once you see what you're trying to do, in this case, it shouldn't be that hard because it works in this case just like your brain wants it to. Like if I tell you to split these up, use all these prime factors somewhere and split them up into two numbers, I'll bet almost everybody in the class, your first thought would be put all the 2's together as one of the numbers and put all the 3's together as the other number. And if you do that, it actually works in this case. 2 times 2 is 4, 4 times 2 is 8. So if I took all the 2's together, that would give me 8. Whatever you don't take for one factor, you take everything else for the other. Well, 3 times 3 is 9. That used all my prime factors. And of course, you can see 8 times 9 is the same thing as 6 times 12. It's 72. But also notice that 8 plus 9 is positive 17, the middle number. Everybody see that? Okay. Every factoring method that I'm aware of requires you to find these two numbers. Now, some teachers tell you just multiply these and get 72, then write every single pair of numbers that multiplies to be 72 until you find the pair that has to be 17. You could do it that way. I just find that if I break it down like this, usually I can figure out pretty quickly how to put those together to come up with the correct numbers. But at any rate, here's where my method is going to differ from what you may have been taught in high school. So some of you might have been taught, and if anybody remembers having been taught this, y'all let me know, because I'm always curious about if we're teaching students to do this. So once we find those numbers, 8 and 9, some of you have been taught to now do this. Rewrite this 6x squared plus 17x plus 12, write it this way, 6x squared plus 8x plus 9x plus 12. And then factor this by grouping. And I'm going to do this real quickly, but I'm not going to explain it because I don't have time to teach this if you don't already know how to do it. That's why we're about to do a different method. But you might remember doing something like this in high school. You use those two numbers to split the middle term up into two terms. I mean, 8x plus 9x is 17x. Then you group each pair of terms with parentheses. And when you look at this first pair of terms, you notice that each term has 2x as a factor. So you factor that out. And you figure out you need to multiply 2x times 3x to get 6x. You need to multiply 2x times positive 4 to get 8x. And so that's the first pair of terms. Do the same thing with the second pair of terms. 9x and 12 have a common factor. Those two terms have a common factor of 3. And so if you factor 3 out, you know that you need 3 times 3x to get 9x, and you need 3 times positive 4 to get positive 12. And then it turns out that 3x plus 4 itself is a common factor. You pull that out front, and it leaves that 2x plus 3 is your other factor. Now, If that was too fast for you and you were just like your head spinning, that's okay. I'm not teaching you how to do it that way. I'm showing you this because some of you may have learned it this way in high school. And if you did, then this might remind you where when I do something different, you don't go, well, I don't remember doing it that way. Maybe because you didn't. You might have done it this way. Some of you may still remember how to do it this way. If you do, that's great. There's nothing wrong with that. But we're not going to do all that. We multiply first times last number. We write out the prime factorization. We use that to find two numbers that multiply to be this thing, add to be the middle thing. Once we find those numbers, here's what we're going to do. Y'all watch real closely. Really and truly, we only need to find two terms here. Let me explain why. We only need to find the first term in one or the other set of parentheses, and we only need to find the last term in one or the other set of parentheses. Here's why. For instance, well, in fact, let's just do it. I'll show you why. So here's what we do. Once we find our two numbers, you always do this every time. You look at the first number in your equation, the coefficient of that squared term, in this case 6. You look from there down to the first of those two numbers you found, in this case positive 8. You look at those two numbers, and what you need to do is find the greatest common factor of those numbers. In this case, the greatest common factor of 6 and 8. What is the greatest common factor of 6 and 8? Biggest number that divides evenly into both of them. Like if it was 6 over 8, what's the thing you would cancel? 2, of course. 2 is their greatest common factor. Whatever that greatest common factor is, in this case it's 2, you always put that number times x first in the first set of parentheses. So the greatest common factor of the first number here, 6, and the first number I wrote down, 8. Their greatest common factor is 2, then I'm going to write 2x in the first set of parentheses. Everybody with me? Now, second moving part. This 2 that I just put there, I'm going to look from that 2 back down to the first number I found, in this case 8, and I'm going to figure out what do I multiply this number 2 times to get this number 8. This number 2, what do I multiply times that to get this number 8? This is an easy question. 4, y'all agree? I need to multiply the 2 that I put here times 4 to get this first number 8, and that's positive 4. Then at the back end of this second set of parentheses, I'm going to put positive 4. Now I should be able to get to the finish line now because everybody look. If I have 2x first in this set of parentheses, what has to be first in the second set of parentheses? 3x, right? We know that because those two terms have to multiply to be 6x squared. And we should all be able to see that, well, what do I need to multiply 2x times to get 6x squared? Well, I need to multiply 2 times 3 to get 6, and I need to multiply x times x to get x squared. So evidently, I need to multiply 2x times 3x to get 6x squared. Okay, if this second set of parentheses ends in positive 4, what does the first set of parentheses have to end in? Positive 3, very good. Why? Because don't these two numbers have to multiply to be this last number 12? Everybody see that? These two numbers have to multiply to be positive 12. Well, then if this one's positive 4, doesn't that mean this one has to be positive 3? So let me clean this up a little bit. So we're trying to solve 6x squared plus 17x plus 12 equals 0. And we have just done that sort of mumbo-jumbo mathemagic to figure out that that factors as 2x plus 3 times 3x plus 4. We're going to do another example in a minute to give you one more chance to look at how this method goes. But remember, we've kind of climbed Mount Everest to get this thing factored, but that's not really, we're not done yet, right? We've got to solve the equation. So now we got to find the solutions to this equation. In other words, we have to figure out what do we replace x with so that 2x plus 3 is 0, and what do we replace x with so that 3x plus 4 equals 0. Anybody got that figured out? It's easier than they think, I think. Any guesses? Okay. If you're kind of like staring intently at that and nothing like no epiphanies are coming to you, look up and I want to show y'all something. Do you agree that if I want to know what value of x makes 2x plus 3 equal to 0, I could literally just write 2x plus 3 equals 0, and I could solve that little equation to find out what to plug in place of x to make 2x plus 3 0, right? And I need to know what value of x makes 3x plus 4, that second factor, equal to 0. I could literally just write that little equation and solve it. So let's see what happens when we do that. Some of you may already have them solved by now. Pretty quick to solve them. I can look at it and solve it. You're going to be able to too once you see what's going on if you haven't already. So when I solve 2x plus 3 equals 0, does everybody agree the first thing I need to do is subtract 3 on each side? So when I do, I get 2x equals 0 minus 3 is just negative 3. And now don't I just need to divide each side by 2? So divide by 2, divide by 2. And so I have x equals negative 3/2 for one of my solutions. Let's go to the other one. Similar deal. I need to subtract 4 on each side. When I do, I get 3x equals 0 minus 4 is negative 4. And then I just need to divide each side by 3, right? And when I do, I get x equal negative 4/3. So now I have the two solutions to the equation. X is negative 3/2. Negative 3/2 is one solution. Negative 4/3 is the other. Everybody see that? Now here's the little trick I want to show y'all. Like, I love math tricks, but I only love math tricks when I know why they work. Because if it's just a trick and you don't understand why it actually works, sometimes it leads you to try the trick. It doesn't work on things that it doesn't work on. Here's why it works. Do you notice? First of all, let me show you what the trick is. So this first factor is 2x plus 3. Notice the solution that goes with it is negative 3/2. Look, if I had just looked at this factor 2x plus 3 and said reverse the sign of the constant term, instead of plus 3, make it minus 3, put it over the coefficient of the x term 2. Just make that plus 3 minus 3 and put it over this 2. Minus 3 over 2, right? And if I do the same thing here, instead of that constant term, which is positive 4, make that a negative 4 and put it over the coefficient of the x term 3, negative 4/3. And that works. It works every single time. Why does it work? Because you can see that when we solve these, once you get these factors, you're always looking at what makes this factor, in this case 2x plus 3, equal to 0. So when you solve that equation, whatever this constant term is, you're going to move it to the other side, right? If it's plus 3, you're going to subtract 3, and that's going to make it be negative 3 over here because it's always being subtracted from 0, right? So you just get that number, this number, plus 3, but with the opposite sign. See, if this had been 2x minus 3 equals 0, I would add 3 to each side, and I'd make it positive 3, right? And certainly at the end, to get x by itself, you're always going to divide by whatever the coefficient of that x term is. Y'all see that? So, you know, if you've got something like let's say you factor one. Maybe it's really hard to factor, but you eventually figure it out, and it looks something like this. And you get to here. Well, you may have gone through hell to get whatever that thing started out looking like factored. That might have been difficult. But once you get here, I can tell you what the solutions to this equation are. They're going to be negative 39 over 17 and positive 27 over 13. So everybody see how we're doing that? All right, let's do one more of these. And then we got to move on. Now, the first thing to notice about this one is it is not set equal to 0. Do y'all see that? I'm going to need to subtract 19x on each side first before I get started to set it equal to 0. So I'm going to go ahead and do that. Again, notice you don't have any first degree x terms over here to combine that minus 19x with on the left. So you're just going to get 15x squared minus 19x minus 10. Equals, of course, 0. That was our entire point, was to set it equal to 0. Okay, I'm going to use my factoring method. So here I go. I'm going to start by multiplying positive 15 times negative 10, which of course is negative 150. But I don't care. I'm just going to say that's 15 times 10. But remember, it's positive 15 times negative 10. So that really is a negative number. I'm going to put a little minus out there to remind myself of that. Do y'all see that that means that here in a minute when we start looking for our two numbers, they're going to have opposite signs, because they'll need to multiply to be this negative number. But at any rate, I'm just going to do the factor tree. Whatever that number is, I know it's 15 times 10, and I know that 15 is 3 times 5. I know that 10 is 2 times 5. And I can't go any further with those. So I'm going to write that prime factorization out. By the way, the order you write them in doesn't matter. You could write 3 times 5 times 2 times 5. My habit tends to be I go from smallest to biggest. So I would tend to write 2 times 3 times 5 times 5. Doesn't really matter what order you write them in. It just matters that you don't miss any of them, right? 2 times 3 times 5 times 5. So I need to use these numbers, these prime factors, to come up with two numbers that multiply to be this negative number. Again, technically it's negative 150. But I'm going to use every one of these prime factors. So the 150 part, I don't really care about that much. I do care, though, one of those numbers has to be positive and the other negative, because they have to multiply to be this negative number. And those two numbers have to add to be negative 19. But these two numbers have opposite signs. So remember, we talked about this just a while ago. If I'm adding two numbers with opposite signs, what am I really going to do? Subtract and keep the sign of the bigger number, right? It's supposed to keep the negative sign. So I know that the negative number has to be bigger. By the way, because I'm going to subtract to get it, I know that the negative number has to be exactly 19 bigger than the other number. Y'all see that? So what are the numbers? Pretty easy to do if you just kind of start putting your pencil and paper to it and try it, right? Positives, and the bigger number needs to be negative. That's the sign we're supposed to keep. So 2 times 3, there's our positive 6. 5 times 5, we're going to make that negative 25. Of course, 6 times negative 25 is the same as 15 times negative 10. They're both negative 150. 6 minus 25, or 6 plus negative 25, is negative 19. So we know we found the right numbers. Now we're going to factor. I'm not going to draw those arrows and gum everything up. We'll just talk our way through it. So remember what we do, and y'all look where I'm pointing. We always look at these numbers. The 15, the coefficient of the squared term. The first number we wrote down, in this case, 6. 15 and 6, what is their greatest common factor?
3.
3. Does everybody say it's 3? 3 times 5 is 15. 3 times 2 is 6. 3 is actually the only thing common to them, right? So 3 is the greatest common factor. Then I write 3x as the first term in the first set of parentheses. Everybody with me? Now, once we've written that 3x term, remember what we do now is we look at that 3, and look where I'm pointing at. We look at this 3. We look back at this first number we found, 6. We got to figure out, what do I multiply this 3 times to get this number 6? 2, I agree. And it's positive 2, right? I need to multiply positive 3 times positive 2 to get positive 6. That positive 2 goes at the back end of this second set of parentheses. By the way, do y'all see that if this had been negative 6, everybody look up because this is important to note. If this number had been negative 6, do you see that I would need minus 2 there? Because I'd need to multiply 3 times negative 2 to get negative 6 if that number was negative. It's not, so it's positive. Okay, then, everything else should fall into place. If this first term is 3x, what does this first term have to be? 5x, of course. Remember, this first term has to be whatever I multiply 3x times to get 15x squared. 3 times 5 is 15, x times x is x squared, 5x. If this last term is positive 2, what is this last term? What do they have to multiply to equal?
Negative 5.
Yeah, negative 5. They have to multiply to be this last number. What would you multiply 2 times to get negative 10? Of course, it's negative 5. Everybody see that? And so our solutions are, reverse the sign, put it over this coefficient, positive 5 over 3. And reverse the sign, put it over the coefficient, negative 2 over 5. And those are our 2 solutions. Everybody see how that goes? By the way, just to show you, we could plug these in and check them. If you go back to the original equation, so you look at those going, well, those are weird looking numbers. Are we sure those solve that original equation? Remember, here's the equation we're trying to solve. So let's try one. I don't know, let's try 5/3. Let's plug, oh, that was not 10x, that was just minus 10. Let's just plug 5/3 in here in place of x and see what happens. So we'll have 15 times 5/3 squared. I just replaced that x with 5/3 minus 10, and we need to know, is that equal to 19 times 5/3. I'm going to run through this pretty quickly because I need as much time as we have left, and I promise we get out of here at 8:15. So I'm going to do this pretty quickly. First of all, 5/3 to the second power is 25 over 9, right? You just do 5 squared is 25 over 3 squared is 9. Or you could think of it like 5/3 times 5/3. Either way, it's 25 over 9. So you get 15 times 25 over 9 minus 10 equals. Here, of course, I'm just going to multiply. That's 19 over 1 times 5 over 3. And 19 times 5 is what, 95 over, 1 times 3, which is 3. Okay, I could get a little help here because I can cancel a 3 on top and bottom. I'm just trying to make my life as easy as I can. 3 goes into 9 3 times. 3 goes into 15 5 times. So I have 5 times 25, which is 125 over 3 minus, does everybody see that 10 is the same as 30 over 3, right? 30 over 3 is 10. 125 over 3 minus 30 over 3. Well, 125 minus 30 is going to give me 95 over 3. And of course, that's what it's supposed to give me, 95 over 3. 95 over 3 is equal to 95 over 3. Then when I plug 5/3 into that equation, it makes it true. Y'all see? So, no, you don't see because I didn't raise my thing up, but now you can see. So those really do work is the point I'm making. Okay, so Do I think that me showing you 2 examples is going to make you a factoring genius on these things if you didn't already know how to do it? Probably not. But it does give you a couple of problems to look at, and a method that always works. It's just a matter of practicing it until you can get pretty fast at finding those 2 numbers, right? Other than that, it's just follow that sequence of steps. Luckily for you, I don't think you'll see too many problems like that where you've got to factor this stuff where you've got some, like bigger number in front of the x squared. But at least maybe that'll give you a little fighting chance if you run into a problem like that. All right, I want to move on. I want to move on with our last few minutes here to this square root property. So here's the thing about this. We've looked at how you can solve quadratic equations by factoring, but that might be overkill for this thing. X squared equals 121. It is quadratic because we've got an x squared term, right? And I actually could, if I wanted to work backwards before I go forward, I actually could solve this by factoring, because y'all look, and I'm going to do this quickly because this isn't what we're going to do, but I just want to show you could. If I wanted to, remember how we say we always want to set these quadratic equations equal to 0? If I wanted to, I could subtract 121 on each side, and I would have x squared minus 121 equals 0. If I wanted to, I could do that, right? If I wanted to just subtract 121 on each side. I actually can factor this, because isn't 121 11 squared? 11 times 11 is 121. So this is the same as x squared minus 11 squared. And we saw last week that we have a way to factor these. A squared minus b squared equals a plus b times a minus b. So x squared minus 11 squared is equal to x plus 11 times x minus 11. And so now it's factored, set equal to 0 and factored. Can everybody see that the 2 solutions are negative 11 and positive 11? So we actually can solve that thing by factoring, but I think it's overkill, because since we don't have a first degree x term here, we only have x squared. We've got it written so it's x squared equals some number. I think we talked about this some last week. Does everybody see that if I took the square root of x squared, I would just get x? So remember, when you take the square root of a square, it's kind of like they just cancel out. But if I take the square root of the left-hand side, I have to take the square root of the right-hand side. And that's what your textbook is calling the square root property. It simply says if you take the square root of one side, you have to take the square root of the other. Just like the addition property that says you can add something on one side as long as you add the same on the other, and so on. But notice if I do that, the square root of 121 is 11. I find one solution, positive 11. And we saw when we solved it by factoring, there actually are 2 solutions, not just 11, but negative 11. Here's the thing you have to remember when you use this square root property. First of all, you can see it's super easy. In cases where it's appropriate to use it, super easy. Get the x squared by itself on one side, a number by itself on the other, and take the square roots of both sides. But you have to remember something we were talking about when we're looking at those complex numbers. 121 has both a positive and a negative square root, and you want both of them. And so that little symbol with the plus above the minus, we usually read that plus or minus. X equal plus or minus 11. It's just a shorthand way for saying, look, there are 2 numbers here, negative 11 and also positive 11. Everybody with me? So like if you had this problem in your homework and you answered it, you actually could use the little plus or minus. They actually have a little button down there you can push that's got the plus or minus thing. I think if you actually type in PM, if you literally just like put your cursor in the little answer box and you type PM, I think it'll actually put that little symbol in there. But anyway, you could write it that way, plus or minus 11, but the homework will also accept it if you write negative 11, comma, 11, right? So this is a simple way to solve equations, particularly when you just have an x squared term and a constant term. Just get the x squared by itself and take the square roots of both sides. If you look at this next one, now this one, you might look at it and go, well, I couldn't really even use that little difference of squares thing because that only works if 18 is a perfect square, and it's not. Technically, there is a way you could factor it, but the factors wouldn't have integers. But I'm going to tell you, don't worry about it. What I'm going to tell you to do is use that square root property. Just add 18 to each side. Get x squared. So when you have one like this where there's no x term, just get the x squared by itself on one side. And when you do, you get x squared equals, well, in this case, you get x squared equals 18. Of course, what I do now, take the square roots of both sides. Remember that 18 has both a positive and negative square root. So the square root of x squared is x, which is what we're looking for. The square root of 18 is plus or minus 3 times the square root of 2. If you don't see that, let's talk about it, because, you know, we've talked about the fact that we've got to be able to simplify these square roots sometimes. If you look at the square root of 18, so just another example to kind of remind you how to do that. You look at the square root of 18. I don't know the square root of 18. It's 4 point something. I know that because the square root of 16 is 4, and 18 is bigger than 16, so its square root must be a little bigger than 4. Square root of 25 is 5. Well, 18 is smaller than 25, so its square root is smaller than 25. It's going to be 4, I don't know, 4.3 or something. I have no idea. But it's between 4 and 5, but I don't really know what. I could use my calculator to get an approximation, but the homework's going to want exact answers in simplified form. And so remember, the trick there is to say you need to find two numbers that multiply to be 18 where one of them's a perfect square. So for instance, you could say 6 times 3 is 18, but 6 isn't a perfect square and 3 isn't a perfect square. But what if you said 9 times 2 is 18, right? And so then you can say the square root of 18 is the same as the square root of 9 times the square root of 2. We don't know what the square root of 2 is. It's a prime number, right? 2 is a prime number. But I do know that the square root of 9 is 3. So I can at least get rid of the radical, the square root symbol over the 9. Kind of stuck with the 1 over the 2. So the square root of 18 is 3 times the square root of 2, but don't forget you want not just 3 times the square root of 2, but also negative 3 times the square root of 2. Everybody see this? Okay, pretty straightforward. Here's a nice thing about using that little method, and it's also a nice thing about having covered section 1.4 last week. If we have this problem, then when we use our little square root property, of course, we're going to get x squared by itself, so I need to subtract 36 on both sides to get started. Incidentally, x squared plus 36 can't be factored. 36 is 6 squared, so x squared plus 6 squared can't be factored. Only x squared minus 6 squared. You can't factor the sum of 2 squares. You can only factor the difference of 2 squares. Everybody with me? And you're going to see why here. When I get the x squared by itself by subtracting 36 on each side, I get x squared equals negative 36. And of course, what am I going to do? Take the square roots of both sides. Remember that every number has both a positive and negative square root, so the plus or minus symbol. And I get x equal plus or minus. What is the square root of negative 36? Well, what's the square root of positive 36? 6. Then what's the square root of negative 36? 6i, right? So this equation, x squared plus 36 equals 0, has two solutions, positive 6i and negative 6i. They're not even real numbers, but they still make the equation true. It's easy to see that too, because if I try one of these in the original equation, I don't know, let's say we try negative 6i. Well, negative 6i squared, negative 6 squared means negative 6 times negative 6, which is positive 36. I squared, remember I squared is negative 1. So I get 36 times negative 1. Well, isn't 36 times negative 1 equal to negative 36? And negative 36 plus 36 is definitely 0, then that's a solution, right? All right. I probably said one more problem. We got 5 minutes, 4 minutes. I can do this. We're going to do one more problem using that square root property. Then we're going to get out of here. And then next week, we're going to pick up the quadratic formula and then move right on to section 1.6. So we got x minus 2 in parentheses squared equals 17. Now, this does not look like what we've been doing. I mean, it's not just x squared equals 17, right? But I think we could still use the square root property here. Everybody okay? Okay. What if I just take the square roots of both sides just like we've been doing? So I know that might seem a little weirder, but look, it doesn't really matter what x minus 2 is. It's all squared. So do you agree that if I take its square root, they're going to cancel and just leave me with x minus 2 without the radical, right? Equals, well, plus or minus the square root of 17. I don't know what the square root of 17 is because 17 is not a perfect square. And do you see this one? I also can't simplify. You know, it's like 17 is a prime number. That's just all I can do with it. Well, I actually can still solve that original equation, though, because do you see, remember what I'm trying to do is get x by itself on one side and a number, or in this case, 2 numbers, by themselves on the other side. So what if I just add 2 to each side of this thing? By the way, I could put plus or minus the square root of 17 plus 2, but usually I would put the 2 in front instead of in back. But that doesn't really matter. I'm going to add 2 to both sides, and when I do, I get x equals 2 plus or minus the square root of 17. And there are 2 solutions there. There's 2 numbers. 2 plus the square root of 17 is a solution to that equation, and 2 minus the square root of 17 is a solution to that equation. By the way, those are both real numbers, right? 2 plus the square root of 17 is a real number. It's an irrational number. You know, you just have to leave it written like that unless you want an approximation, which again, in a science class, they might want an approximation. In math, we like the exact answer. That's because we always like to be exactly right, whereas science is usually good with being kind of right. That's what I think. They're good with being pretty right. They're good with deciding how right do we need to be to feel safe and making sure they're at least that right. Okay, y'all, we're going to bail out of here. We're going to start off next week with the quadratic formula. Some of y'all may have seen this before. I'm sure you've all seen it before. Some of you might even remember having seen it before. We're going to look at how to solve quadratic equations using this formula next week, and then we're going to move right on to 1.6. So you want to know where you need to be at next week to feel caught up. Well, you need to have 1.2 and 1.4 finished when you come to class for sure.